All right, welcome back, class. I believe the board the whiteboard is is clear. There are a bit of some mathematical things, but nothing rocket science. It's just what you'll see that it's just familiar mathematics. So these are the two equations that we had. Yeah, that this the rate constant uh, for the substituted benzene is equals to that gradient rho multiplied by the log base 10 of the equilibrium constant, whereby you'll be looking at that one which has the substituted benzene. How does it ionize in water? So in this case, in one case, you are looking at uh, how it reacts with other compounds. In another case, you're seeing how it ionizes in water. The same thing, the rest of the structure does not change. In one case, you are seeing how it reacts with other compounds. There is the rate constant. How it ionizes in water, there is the capital K. And then you compare with the rate constant for the unsubstituted benzene. There's the gradient, and then multiplied by the log base 10 of the ionization constant for the benzoic acid. So the equation is of the form y is equals to mx plus c. So there's equation 1 and there's equation 2. So what I'm going to do is I'm going to subtract equation 2 from equation 1. So you're going to have log base 10 of kx minus log base 10 of kh. This small k, the rate constant, is equals to, in this case, this one plus c, and then I'm going to minus c. So c and c are going to cancel. I'm going to be left with the rho log base 10 of the equilibrium constant of kx minus rho multiplied by the log base 10 of kh. Yeah? Yeah. So based on what you know about logarithms, if I'm going to have minus, I can put the log base 10. I'm going to have this one, kx over the kh. Yeah, these are rate constants. Yeah, please note this. Yeah, so is equals to, in this case, rho is just constant, and then we could put log base 10 of the kx minus log base 10 of the unsubstituted benzoic acid. Now, from what we had known, pKa is minus log base 10 of the ionization constant. So that tells you that that uh, for many compounds, what I can get is the pKa. There are many books which contains the pKa value. So that's what you can use to be able to equate as opposed to the ionization constant and the rest. So if I'm just going to rearrange the same equation again and say log base 10 of the rate constant for the kx and the kh is equals to rho. In this case, what I'm going to do is I'm just going uh, to express this equation in terms of uh, in terms of the pKa. You're going to see that this minus log base 10 of kh, I'm going to put it here, and then this plus, this one here is plus, is the same as minus minus, yeah? So that I'm going to have everything in terms of minus log base 10 of something. So there will be minus log base 10 of kh minus log base 10 of kh. So minus log base 10 of kh, that is the pKa of the unsubstituted benzoic acid, sorry. And then this minus log base 10 of kx is the pKa of the substituted benzoic acid. So this terminology whereby you've got the pKa of the parent, I mean of the benzoic acid minus the pKa of the substituted benzoic acid, is what was given the symbol of sigma. So the Hammett equation now simplifies to log base 10 of the rate constant of kx over kh is equals to the rho, which is the gradient multiplied by the x-axis, in which it is sigma. Can you see that? So this is now what's going to be called the Hammett equation. And I've just given an example here. Hopefully you'll be able to zoom it and see these figures, but I hope me, I can see from me, I believe everything is clear. But I think later we'll give the PDF of some of these things I'm talking about. All right. So here I've just given an example. This is a typical example. What you're going to see is that in addition to the rate, also the Hammett equation, it can be given an experimental data, and then you can be told to plot and then determine probably the gradient or some other things which you can determine from the graph. So in this case, this para-substituted benzoic acid, you are seeing how it's going to be ionizing in water. Excuse me. So, excuse me. So these are the various groups attached. There is the nitro group, there is the cyanide, there's the chloride. Uh, in this case, there is no substituent. This is the, what do you call, the reference group. So in this case, it's telling you there is no substitution. I'm talking about benzoic acid. Yeah. So that you're seeing the sigma relative to the benzoic acid, like in this case, it will be the one for the benzoic acid minus the one in which the x is 0, so that you are seeing the sigma is 0. Can you see that? Okay. So in this case, there is the methyl group, and then there is the methoxy group. Yeah. So this is the ionization constant, 3.55 times 10 to the power minus 4. That's the pKa minus log base 10 of the Ka. And then there's the sigma. I mean, there is then there is the sigma. So in this case, you can see sigma. I think what I've done, perhaps this column would have been here, and then this one for the pK would have been here, because from the sigma, what you are seeing is this. Sigma is the pKa of the unsubstituted benzoic acid minus the one for the substituted one. So that in this case, what I'm going to get here, if this is, if for example, I'm dealing with 4.0 as the pKa for the benzoic acid, so that in this case, what I'm going to do is that for example, for this one, it will be 4.2 minus 4.37. So I'm going to get what? Minus 0.17. So this is 4.2 minus 4.47. I'm going to get negative 0.27. So if I'm going to get 4.2 minus 3.5, I'm going to get a positive figure. This one a positive figure, something like that. Yeah. So once again, you can put this log base 10 of Ka on this other column, and then the pK, because the pK will be the one which will be giving, which will be giving the sigma values. Can you see that? Which will be giving what? Which will be giving the sigma values. Yeah. Are you okay with that? Now, what I wanted you to see now, and that's something which you ought to say. And this is something very important, and I hope you'll be able to have a pen and look at it. The more the group attached to the benzene group, the more it donates electrons, the more negative the sigma value. Yeah. The more the group, the more the group attached to the benzene group donates electron to the benzoic acid, the more negative the sigma value. And the more it withdraws electrons, like in this case for the nitro group, the more positive the sigma value. Yeah. So can you see that? That in this case, even if you are not given the groups, you can look at the sigma values and then say, hey, relative to this one, this group does not it withdraws electrons, but not as great as the one which is on top of it. This one which is negative here, this one we here which is more negative, donates electrons better than the group which is has got a less negative figure. Are you writing it down? Or maybe you can rewind the video a bit, yeah? So this positive and the negative figure, they tell you something about the electron density around the group which is around the reaction center. Yeah? Can what I'm saying is this that that the Hammett equation is not just about plotting some figures here. What you have about the sigma, and later, which we'll see the gradient, which are going to be calling rho, they are going to tell us something about the electron density in the reaction which you are dealing with. Okay, okay? So this rho and the rho and the sigma are not just anything to plot. Now we are focusing on the sigma. But far more information, far is found by rho, by studying the rho. And this is what really brought a lot of things about understanding mechanism based on this Hammett equation. You're going to look at it. But once again, there's a book dedicated to the Hammett equation only. I uploaded it on the Google Docs, yeah? It is based on the Hammett equation. It goes far deeper than the things which you are going to cover in class. The things which I'm only going to be covering in class are the things which, because we're just having a limited period up to when the exam will be, which will be starting next year. But before then, what I wanted you to say is this: there's a lot about the Hammett equation, but we'll just look at just a few things. But you'll be able to look at that book and understand more about the Hammett equation. But there's a whole book dedicated on the Hammett equation. So the sigma tells you something about the electron density of the groups attached to the benzene ring. And then later, we look at, later, once we are through with the various information about what? About the electron density of the groups attached to it, we'll see what does the plot, what does the gradient tell you about the mechanism of the reaction. Are you okay? Are you surprised? Such a thing, such a simple equation is going to tell you something about the mechanism. And just come to it that the pKa is not a simple thing just as the pH, which just like the concentration of the acid. pKa is related to the structure of the molecule. So every hydrogen or has got a unique pKa value. Has got a unique what? pKa value. So that's why what you're going to see is that the pKa is related to the mechanism. And as I mentioned, please, if you can get time, look at that book, Electron Flow in Organic Chemistry. That tells you how you can use the pKa to understand mechanisms. And if you combine it with the molecular orbitals in that book and the Lewis structure and everything and those curly arrows contained in that book, Electron Flow in Organic Chemistry, I want to tell you, you will never have problems with the mechanism. That book, Electron Flow in Organic Chemistry, is the world leading book on mechanism. If you're going to look at it, you're not going to have a problem on mechanism. Once again, it's on our Google Docs folder. Yeah. Okay. So uh, so in this case, we've now seen uh, the sigma here. So in a short while, we'll also look at at another table showing what? Showing this sigma value. What this data uh, was good to generate is want to generate an actual table to be able to determine what this relationship. So we need to find out the rate constants. This one was just to give us the equilibrium constants and therefore generate the 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 x-axis. So these sigma values are for the x-axis for the table, no, for the graph that we want to draw. So these figures are for, this is the x-axis, because these are the sigma values. Can you see how this question can become complicated? So you can be given the pK values, or you can be given the Ka. It means you're going to determine the log base 10 of the Ka, convert it into the pKa, and then determine the sigma. The sigma means you look at the row where there is the hydrogen, which is your reference point, and then you subtract the other figures relative to it. So some are going to be positive. It's telling you the group is donating, no, is withdrawing electrons uh, uh, from the reaction center. It's withdrawing electrons. It's like it's an electron withdrawing group. That's what it's telling you. This is the x-axis which we have generated. Now, so we look at another table which will now give the rate constant. So based on the rate constants, we look at the actual rate constant. For example, like for the nitro group as it's attached to the benzene group, and then you're going to put it relative to the rate constant where there is the benzoic acid, and then look at the base 10 of that one, and then plot against these sigma values, and then that will give us the what? The raw value as as the the gradient. Yeah. So you've been able to put this figure, and then so later, so you're going to look at another table. It's not going to contain a lot of things. Just going to contain the new sigma values which you have generated, and then we'll now look at one in which they are the rate constants for this reaction, in which probably you may have this one in which there is the y, and then probably you've got the ester, because you need to look at two different reactions, one for this ionization, and two in which the group which is attached to the benzene is reacting with something, which is the reality of what you get. You don't normally get the ionizations. These ionizations, they give you the the x-axis. Now we want to look at what is determined by the rate constant. The rate constants you determine by the concentrations for the formation of the products, or for the what? For the decrease of the starting materials. All that information you can get experimentally. In other words, I'm telling you, Master of Science students, that uh, based on just simple reactions for what you're doing, you can generate a good number of papers based on a mechanism which you may be trying to determine if you're doing a research project. Yeah, keep note of that one. Uh, so the Hammett equation, especially if you're dealing with benzene substituted products, especially for the natural products, they contain a lot of rigid systems. Now, this equation which I'm telling you relates to the rigid systems of the substituted benzene, whereby it's attached at either the meta position and the para position. So it has limited scope. If you have the group attached at the ortho position, or it is at aliphatic, then this equation does not apply. Please note of that. Please take note of that one. So we've now generated the x-axis. So want to look at another table whereby it's showing the rate constants, and then see what the plot can tell us something about. Yeah, are you okay with that? So we'll stop there, and then we'll pause there, and then we'll proceed shortly. Yeah?